Hello everyone, I'm Tianchen from University of Rochester. Today, together with my partner Yufeng, I will present our work, Mesorasi, Architectural Support for Point Cloud Analytics via Delayed Aggregation. This is a joint work done by our team at Rochester and ARM Research. Are you still seeing the world through a flat screen? Even a machine has a better solution for that. And that is done by perceiving the world using point cloud data. Point clouds are essentially sets of 3D coordinates that represent the real-world objects, and they are produced from 3D cameras and sensors. Nowadays, point clouds are widely used in critical applications such as autonomous driving and robotics. Recently, for tasks like object detection and classification, people have developed many deep learning-based approaches for those tasks. And our focus here is to improve the performance and energy efficiency. And with all the existing DNN accelerators, a simple question here is that, can we directly use them on point cloud workloads? So to answer this question, we first need to understand how do point cloud networks work? It turns out that there are mainly 3 key operators. Here, we'll go through them one by one. The first operator is neighbor search. So what neighbor search does here is to find the neighboring points of some other points. Here's an example. So neighbor search is given a set of points, and then it is instructed to find the neighboring points of P1 and P8 among the other grid points here. Once the neighbors are found, it will return the neighboring information. In conventional DNNs, there's really no need to do an explicit neighbor search. And the fundamental reason here is that pixels on 2D images are very regular, while in our case, the points in 3D point clouds are irregularly scattered in memory. And the second operation is aggregation. Here, as a reminder, all these points are essentially feature vectors. And also remember that the previous operation neighbor search finds all the information of neighbors. They are essentially just groups of references to the actual data points. So what aggregation really does here is to use those groups of references to access the memory and get the actual feature vectors. And then it will do some post-processing and aggregate them together. So since we're aggregating vectors together, we will essentially get a matrix here. So here we call it a feature matrix. And I will use an example to illustrate how P1's feature matrix is aggregated. So first, it will access the memory to get a feature vector of P0. Note that P0 is a neighbor of P1's. And then it will do a normalization step. So what it really means is to minus P0's feature vector by P1's. And this is done for all the neighbors of P1. Then we will have the feature matrix of P1. And this step is done for all the selected points here. And once we have all the feature matrices, the next step is feature computation. So yes, all these feature matrices will be fed to the neural nets for feature computation. And note that this is done for all the vectors in the feature matrices. And once we have all the new feature matrices ready, they will be reduced to new feature vectors. And usually, this reduction operation here is a max operation. So now, with all the 3 key operators, we can compose a point cloud network layer. Getting back to the previous question, the simple answer is no, there are not enough. And the main reason here is that we have new operators, neighbor search and aggregation. So based on our characterization results, these 2 operations together take a non-trivial portion of the total execution time. And what's even worse is that on today's high-end mobile GPUs, these point cloud workloads are still very slow. So what can we do to optimize? So remember, this is how a point cloud network layer looks like. So here, we have developed an algorithm optimization that can tremendously reduce the workload of feature computation. So the input to this step are feature matrices produced from the previous step. And the computation here is mainly matrix-matrix multiplication. And also remember that all these feature matrices are made up of individual feature vectors. And also, these vectors are originally normalized from individual point features. So mathematically here, we can sort of decompose the computation into two individual steps. And that is to say, we can do feature computation for P3 and P1 individually, and then we can do the normalization later. So by exploiting this distributed property here, the benefit is tremendous. So first, it effectively introduces data reuse opportunities. And more specifically, in our example, the feature of P3 and P1 calculated can be used multiple times. And then in real applications, we have found that each point is on average used for around 30 times. And with our optimization here, this directly translates to up to 90% of compute saving. What is more, it also eliminates the dependency between neighbor search and feature computation. And more specifically, in the previous algorithm, we cannot do feature computation unless we know that P3 and P1 are the same. And now, since we are doing feature computation on individual points, we don't need those information to do feature computation. However, here the problem is that with nonlinear operations such as ReLU in the networks, the equation on the left side does not strictly hold. However, here the problem is that with nonlinear operations such as ReLU in the networks, the equation on the left side does not strictly hold. Still, our experiments indicate that by retraining the optimized networks from scratch, the accuracy hardly drops, and in some cases, it even increases. So here, this distributed property still approximately holds. With all of that, we call this optimization delayed aggregation. So the reason is that we can now do neighbor search and feature computation in parallel prior to aggregation. We're essentially delaying the aggregation to the very end of the network. So as we apply the optimization, we can see tremendous performance gain. So here, as we do the characterization again, we can see that the computation time of feature computation has dropped tremendously. However, here, the aggregation time also increases. And from now on, my partner Yufeng will introduce how do we solve this problem by hardware co-design.
Now, Tiancheng has already introduced the first part of our framework, delay aggregation algorithm. Next, I'm going to introduce the second part, our hardware design. As a recap, let's review the process of aggregation operation again. First, the labor index table will use each central point along with its labor indices to access the point feature table. And then gather the labor features from the point feature table and store them to the labor feature matrix. Notice that the memory access to the point feature table is highly irregular. After get the labor features, each labor feature will be normalized by subtracting its central point feature. This operation will repeat for all entries in the labor index table. In the end, each point will perform a reduction to find the maximum value. Based on the accessing pattern of aggregation, we design our aggregation unit as following. It has a neighbor index table to store the central indices and their own labor indices. Each time, the address generation will read one row from the labor index table and try to access the point features from the point feature table or from the global buffer. Here, point feature table is designed as B independently addressed single port SRAM, similar as B port B bank SRAM with no crossbar. All banks will connect to a reduction unit to perform max operation and shift generate maximum to the shift register. We wire the shift register back to the reduction unit in case we need to perform multiple rounds of reduction if necessary. In addition, we also use a mask to load central features vector to the standalone shift register. After complete aggregation in two shift register, this two vector will perform a normalization, which is essentially a subtraction to store the result to the global buffer. In our paper, we have a more detailed information on how to reduce the size of point feature table and effectively compute aggregation. Please check our paper for more details. The overall Mesorasi architecture design is shown here. We use DRAM as primary storage for input, kernel weights, and intermediate data. On our Mesorasi SoC, it consists of a GPU and a DN accelerator, NPU, which is built on top of today's SoC. We use GPU for neighbor search execution and NPU for future computation and aggregation. On our Mesorasi NPU, it has a historically-based compute unit to support convolution and MLP computation with a global buffer to store inputs, weights, and feature maps. Finally, we augment our aggregation unit to effectively execute the aggregation operation, which we have already introduced in the previous slides. Our aggregation unit provides efficient data accesses for aggregation with a little area overhead. Notice that the only highlight blocks are our extension, and it can be easily integrated with conventional NPU without modified NPU. In this paper, we assume a historically-based NPU, but other NPU architecture works as well. Now let's see our experimental result. In our experiment, we evaluate on 3 different point cloud applications: classification, segmentation, and detection. And we use 3 datasets: ModelNet, ShapeNet, and Kitty dataset. We evaluate 8 point cloud models. They are all state-of-the-art algorithm and widely adopted by the point cloud community. In addition, we also open source our code on GitHub. First, let's see our accuracy result. So the x-axis shows different networks and the y-axis shows accuracy. We first show the original result. Next, we will show our result. As we can see, our delay aggregation can achieve similar accuracy as the original algorithm. Next, we will show the speed up and energy saving on the off-the-shelf mobile GPU, NVIDIA TX2. Notice that the result here doesn't have our new hardware support. We first show the speed up. The x-axis shows different networks, and the y-axis shows speed up. On average, we can achieve 1.6 times speed up. Next, we will show the energy saving. On average, we can achieve 51% of energy saving. In addition, we also evaluate our newly designed hardware. The hardware baseline is a generic NPU plus GPU SoC, and we have 2 variants in our evaluation. The first one is Mesorasi software, only use delay aggregation without aggregation unit support. The second one is Mesorasi hardware, which use delay aggregation with additional aggregation unit support. Both the baseline and our 2 variants implement a 16x16 historical array. It is a cycle-accurate simulator parameterized with data from the RTL synthesis. The RTL is implemented using synopsis synthesis and layout in 16 nanometers technology. Here we show the speed up. Again, the x-axis shows different networks, and the y-axis shows speed up. As we can see, our Mesorasi software can only achieve 1.3 times speed up. With additional hardware support, our Mesorasi hardware can achieve 1.9 times speed up. Here we show the energy saving. Again, the x-axis shows the different networks, and the y-axis shows the energy saving. Without hardware support, Mesorasi software can only save 22% of energy saving. However, with additional hardware support, we can achieve 38% of energy saving. So in summary, with the explosion of 3D sensing device, point cloud algorithm present an exciting opportunity to transform perception ability of future intelligent machines. And our delay aggregation algorithm decouples the neighbor search and feature computation and significantly reduces the overall workload. In addition, our hardware support further maximizes the efficiency of delayed aggregation. That's the end of our talk. Thanks for watching.